On January 15, 1908, a young boy named Edward Teller was born in Budapest, Hungary.
Congratulations. It's a boy.
Thanks, Doc.
Teller got his PhD in theoretical physics at the University of Leipzig in 1930.
Congratulations, Dr. Teller.
Thank you, Professor.
Around 1935, Teller moved from Europe to the United States and became a professor of physics at George Washington University.
And that is how he solved Newton's second law. Teller's career really soared when he was asked to work on the Manhattan Project in 1942. Here are the plans for the Manhattan Project. The power, when dropped, results in a sudden release of energy upon the fission of the nuclei of plutonium or uranium.
This is great. We'll be sure to use it on Japan. This all to bring an end to World War II. Now, what does it do? An atom bomb works by initiating a nuclear chain reaction, which releases a huge amount of energy relative to conventional explosives. Per unit volume, an atom bomb may be millions or billions of times more powerful than TNT. The first atomic explosion occurred on July 16, 1945, at the Alamogordo Test Range in New Mexico, during a test called Trinity. It was developed during the top-secret Manhattan Project, which was directed by General Leslie R. Groves of the U.S. Army. Nuclear reactions occur when neutrons are fired at closely packed atoms with heavy nuclei. These heavy nuclei break apart into lighter nuclei when hit by a neutron, in turn generating more neutrons which bombard other nuclei, creating a chain reaction. This process is known as fission. By breaking down the nuclei themselves rather than releasing energy through a conventional chemical reaction, atom bombs can release more than 80 terajoules of energy per kilogram. In the earliest bombs, the chain reaction was initiated simply by firing two half-spheres of high-purity uranium isotope at one another in a small chamber. In updated designs, a uranium or plutonium bomb core is surrounded by high explosive lenses designed to compress the core upon detonation. The compressed core goes critical, initiating a chain reaction that persists until many of the heavy nuclei have been broken apart.
Let's see how it worked.
This bomb inspired Teller to make a bomb of his own, the hydrogen bomb. The hydrogen bomb is by far the most destructive weapon that mankind has ever invented. It is the most powerful type of the nuclear bomb, in some cases reaching more than 2,000 times the yield of the nuclear bombs dropped on Hiroshima and Nagasaki, Japan. Unlike the first atomic bombs, which release energy by fission, or breaking apart of heavy atomic nuclei like uranium and plutonium, a hydrogen bomb releases energy by fusing together light nuclei like tritium or deuterium, converting even more matter into energy. When President Truman authorized the dropping of the atomic bombs on Hiroshima and Nagasaki, he said that the weapons used the same power as the sun, but that was not actually true. The sun uses nuclear fusion, not nuclear fission. The hydrogen bomb, however, really does release the power that fuels the sun. Nuclear fusion involves creating heavier elements out of lighter ones by joining atomic nuclei together. In the sun, this mostly takes the form of fusing hydrogen nuclei to form helium. A fusion reaction is very difficult to start because nuclei are positively charged and therefore strongly repel one another through the powerful electromagnetic force. The nuclei of elements heavier than hydrogen are held together by the strong nuclear force, which at this scale is much stronger than the electromagnetic. The strong force, however, is only significant over extremely short distances of around the size of an atomic nucleus. To start nuclear fusion, nuclei must somehow be brought very close together. In the sun, this is achieved by gravity. In a hydrogen bomb, it is achieved by a combination of extreme pressure and temperature brought about by a fission explosion. A hydrogen bomb is therefore a two-stage weapon. An initial fission explosion causes a fusion explosion. A fission bomb primary is detonated in the normal way, which then compresses a fusion fuel secondary and ignites a uranium spark plug, which fissions and subjects the fusion fuel to the heat necessary to begin the reaction, about 20 million degrees Fahrenheit. In the sun, the main fusion process results in 4 hydrogen nuclei, which consist simply of a single proton, combining to make a helium nucleus, which has 2 protons and 2 neutrons. The heavier hydrogen isotopes deuterium and tritium, with 1 and 2 neutrons, respectively, are created at intermediate steps. It is impractical to try to replicate the whole process by starting with ordinary hydrogen, but the fusion of deuterium and tritium can be achieved. An early test involved using these gases in liquefied form, but a crucial modification was the use of the solid lithium deuteride, a compound of lithium and deuterium. Under the conditions created by the initial fission explosion, the lithium is transformed into tritium, which then fuses with the deuterium. The first true hydrogen bomb test, Ivy Mike, was on November 1st, 1952. It detonated at Eniwetok Atoll in the Pacific as a part of Operation Ivy. The bomb exploded with a force equivalent to 10.4 megatons of TNT, over 450 times more powerful than the atomic bomb dropped on Nagasaki during World War II. Using liquid deuterium as fuel, this hydrogen bomb required 18 tons of refrigeration equipment. It was not a practical weapon, but it proved that a fusion bomb of enormous power could be built. You are about to see the first ever hydrogen bomb test.
Begin the countdown.
10, 9, 8,
7, 6, 5, 4, 3, 2, 1.
Edward Teller died on September 9th at his home on the campus of Stanford University in California, having had a stroke a few days earlier.
What is love? Baby, don't hurt me. Don't hurt me.